Hello everyone, and today we're back again on AtCoder Beginner Contest 322. So we have 30 seconds till the beginning. I will be using the CPA Judge extension as always, combined with the competitive companion extension. Check out the other videos on my channel. I sometimes explain some concepts in programming and electronics as well. So this contest is always every Saturday, so it's really fun. It's really educational, and yeah. So let's go and try to solve the problems. You're given a string S consisting of ABC. Find the position where ABC appears first as continuous subsequence, or it doesn't appear. I think this font is good. If the substring starting at that position is ABC, then I want to print out and return. Otherwise, I'll just print out -1 here. Position substring. Oh, it's 3, of course. Okay. You're given two strings, S and T, consisting of lowercase English letters. The lengths of S and T are N and M, respectively. S is said to be the prefix of T if the first N characters of T coincide with S, or the suffix of T. S is both prefix and suffix. Print 0. S is, so you just have to check is this. Just a few checks. If the suffix is equal to S, if the prefix is equal to S, if the suffix of T is equal to S, that is M minus N plus 1, I think it should be equal to S if both of them or neither. So if prefix and suffix, see out, what is this, 0, else if prefix, see out 1, else if suffix, see out 2, else see out 3. ABC, this is not correct. Right. M minus N. I think this should be okay. AtCoder Kingdom holds a festival for N days. On M of these days, namely the first M days, fireworks will be launched. Oh, not the first M days. These are specific days. It is guaranteed that fireworks will be launched on the last day of the festival. for each of these through n, so for each day, how many days later from the ith day will fireworks be launched for the first time on or after the ith day? If fireworks are launched on the ith day, it is considered to be 0 days later. Yeah, okay, easy. So there's n and m. So we just have a vector. There's m of these. Then minimum days n. I start from the last guy, go here, and then say that minimum is minimum of minimum at 5 minus 1. Of course I can start from what I can have is like another array. It's easier this way, that this is the answer array, and then for each of the m things, I will say that the answer of a of I is a of I. For each of the m things, I can say that the answer is a of I. Then go from end to beginning, say that the answer is the minimum not the answer at I is the minimum of answer at I plus 1, and then we just want to print out the answers, but the answers are printed in the way that answer of I minus I. Wait, this is the second. Oh, it can be solved with two-pointer technique as well, but didn't want to write it. A polyomino is a puzzle piece in the shape of connected polygon made by several squares, connecting several squares by their edges. There is a grid with 4 rows and 4 columns, so 4 by 4 grid, and 3 polyominoes that fit the grid. The shape of the ith is represented by 16 characters. They describe the state. If it's a square occupied, okay. If you want to fill the grid with 3 of these so that all of the following conditions are set. Must not overlap, must not stick out of the grid, may be freely translated and rotated, but may not be flipped over. Can the grid be filled? So there are what? 3 of these, polynomial, 3 of these, and can the grid be filled? Okay. So how many? What are the combinations here? For each of these three, there is rotation, there's translation, there's a lot of stuff going on. Technically, there is. Oh, there's a lot of these. So there are four to the 3, there's the rotation. There's 64 rotations times 64 rotations times okay, so there's like 4 and 4. There's 3, 4. There's like 7 or 8. Let's say 8 times 8 on this, so 64 again on each of these. But these are so 64 things. But then these are translated each of them. So that's cubic. And then you have to iterate over 16 times 3, which is a huge, it's not that huge actually. Might just pass. But another thing is just to make them smaller and then iterate over like all of the possible things, flipping them. But it's much easier to rotate end by end matrix than to rotate this thing here. If it's not, it has to be brute force. It has to be just brute force, but it's implementation problem. So C got accepted. Okay, so this implementation, just heavy implementation. E, what is E? Is planning to develop a product. The product has k parameters whose values are currently all 0. The company aims to raise all parameter values to at least p. There are n development plans. Executing the ith plan increases the value of the jth parameter by aij. Okay, so there are some plans. There's 100 plans with some cost. Okay, a development plan cannot be executed more than once. Determine whether a company can achieve its goal. Find the minimum total cost. So the development plan has only 5 things that are considered that will be changed. These 5 things will be changed with the cost of CI. Has k parameters. So k parameters. So each has 5 parameters only. 5 parameters only. Why such a small number? The cost, if they are increased by aij is also up to 5. So how many variations is there? Is the 5 to the 5, right? 3000 such variations. So 3000 different development plans could be issued, but there is okay, so let's consider some DP. So there are 5 and 5, so we want only at least 5, so we want, okay, 5 5, yeah, okay, so DP, yeah, this is a much easier problem to write. So DP with 5 dimensions, DP with essentially k dimensions, each reaching k parameters, each reaching p, right? So that is fine, I think. Okay, what am I doing? Int n k p. So there's this dp up to 5, right? No, up to 6. There's this dp. Then we want to mem set it km n. And this is the cost, which is then is long max. Okay, so this is the dp, the 5 dimensions, and then for only dp of 0 0 0 0 0 has cost 0. Now for all of these, I will go for all of n. Okay. And compute the following. For all of n there, first we need to read that stuff. I can read it here as well. Okay. Or should I read it? Ah. Let's read it here. Okay, so now the dp is, oh, Now the DP is just okay. We want to update the DP, which we will push on the DP. So we will say the following: I plus A of U 0, but this can be more, so I can just limit and say it like this. Or minimum of this and the P, right? Of course you can do this with for loops, but I'm lazy. B, C, D, E. So DP of A, B, C, D, E. This is J, of course. This is K. This is M. This is N. So we add something to this DP, and this DP is my DP, I, J, K, M, N, plus the cost of U, and the cost of U is where? It's the first element. Now I just need to inline void U main if B is bigger than A, if A is bigger than B, A is B. And then now we want to have that at least P, so we want just to do DP of P, 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 I think. And this could, if answer is long maximum, let's say 10 to the 18. Here, let's say 10 to the 18. This is due to overflow. If answer is 10 to the 18, then it's -1. Otherwise, it's P is what? P is P5. Yeah, P is 5. Okay, we read all of these, right? We read them as it should. I mean, accessing here, that will never be enough. So it's my here. Oh yeah. What if they're less than these dimensions? So if there are only like 3 dimensions. Let's, instead of all of these, let's write them in a nice for loop. This is or this will be faster, I guess. what letter should I use here? T is to the dimension. Then this is minimum of, so int so this is like destination, right? Why? What is too many initialization? Oh yeah, this is T. Now I want to mask at T plus this minimum, and then this is destination at T. And now the DP is destination at 0, destination at 1, destination at 2, destination at 3, destination at 4. This remains okay. And now this is again like I can have this destinations here. I can copy this out. Okay, so I don't need the mask. I just need to say destination at T is equal to P. So this will be my mask for the destinations. Then I get the DP. The DP is this. Okay, so 171. Says that 171 can do it. But what is this? The product is all currently is the cannot be executed more than once. Determine whether the company can achieve and the minimum total cost. So the goal is to get all of these to 5, right? So are these all enough to get to 5? No, this end thing is not enough to get to 5. This end thing is not enough to get to 5. What? How are you getting to 5? I don't understand. That does not make any sense whatsoever. 36 cannot be a solution. Thirty-six cannot be a solution. Wait, let's say like this. So some solutions cannot exist, right? But some can. Right now, to claim that there exists such a solution, it doesn't exist. Oh, okay, this exists because I can make more of these, yes. But now this 36 means that I don't well, I don't see how this could turn to be here. 36. Mask should be 0. This as well should be 0. Oh, I see. Okay. But 36 doesn't make sense. Because there's no 36 here. Let me think about this. Destination is 5, 5. And destination at 1 and at 2 here. Okay, 185. 61. And then 36. How so? What grounds? But I don't understand how is this possible even. Like how? We only once iterate for these. Oh, the way we iterate them. Oh. This thing. We should iterate from the max minus 1 to 0. I see. J, K, M. It's faster this way. I know it's slow, but what can I do? 5-dimensional DP. Okay, now this should work. Okay, now we Okay, now we print something that now there's some overflow here. TP minus 1 destination. There shouldn't be an overflow here. Oh, of course. Okay, let's see problem F. You're given a string S of length n consisting of zeros and ones. Process Q queries in the order they are given. Each query is represented by a tuple SCLR for C1 for each integer for this. If S is 1, change it to 0. If it's 0, change it to, so flip this. Let T be the string obtained by extracting the substring, the LNR substring. Print the maximum number of consecutive ones in T. Well, consecutive ones doesn't kind of change, right? Like, I mean, it does change, but oh, it does actually. But that's like coloring, right? Like, okay, E gets accepted. Let me just see how's the standing doing. Okay, practically. So, okay, interesting problem. Consecutive ones at that array. Can we do? So we can't do some square root decomposition, right? It's too much. Can we have a segment tree that will change, that will flip these to zeros and ones? This can be done by like a Boolean thing. And then have like a, like this min prefix max, prefix and suffix for each node. What is the minimum maximum length of each node? And then you want to have like a value, which is the answer. And that's pretty much it, right? I think so. I think I can solve this in a segment tree fashion. It will be a little bit hard, but just, I think, an ordinary segment tree. Okay, so we need like a build function that will build segment tree, and the build function is going to just require the string s. This is s at l, so this is dot value s at l minus, not dot val, maybe dot character, some like character here, minus 0, and then we want to just pass the string as reference to the build function again. Of course, this is doing this. So that's the build function. The thing is that, okay, so here's the thing. 4 times 7. Here's the thing. The value is fine. This is like the answer, right? for this node. Then there's like a character. Then there is so we'll fix this here. Then there is like flip. Oh, because this is updates a whole thing, we need to like a lazy. Right, but can we do a lazy here? Is it even possible to do this? I think it is possible. Right? Yeah, I think it is possible. So let's do a lazy. Well, we don't need the signature. We need lazy. So the value, this is the value. This is like the lazy. The value is of course 0, the lazy is 0, but then there is suffix, there's like prefix, and there's suffix prefix, the value, yes. So that's fine. That's fine. So we don't want segment tree, we want lazy segment tree. Okay, so now we will convert S to an array. Then the point is, for each query we will just call, for this query we will call update, and this will be, okay, the update function doesn't necessarily need to look long. Update function will just update, will toggle the value, right? Doesn't even need this. Let's make it cleaner. So the update function will update from L to R plus 1. So then this is the case. And this would be a query function from L to R plus 1. And I can just see out this. So see out the query function. If it's outside, it's 0. Else we return the value. So the value. Okay, now we need to do the signature magic. when we merge, what happens when we merge? Okay, what happens when we update a value? The lazy thing changes, right? The lazy thing changes. When we apply a value, the value changes. The value changes when we apply. If lazy is default return. If this is the case, if L and so we need to propagate the lazy value. So that's just that. And the lazy is again shifted like this. We're just set to 0. Set to 0. Now, the thing is that when I apply the lazy button to the bottom, it's so I apply the lazy to the other nodes. The thing is that it may be actually wrong. So here we know that we have flipped, right? But we need to know what is the best thing now that end up with zeros here. The prefix and the suffix with zeros have to be initialized. So not only that this has to be button like what if there's ones and what if there's zeros? Now the merging is pain. Okay. Okay, so we calculate the suffix is the biggest. So okay, let's merge. L dot suffix first, because we push here, we merge at the end, right? But wait, we will update this. And do need to push, right? Wait. We do need to push here. This is something wrong here. Okay, so update. We push down, right? We push down. But if there's nothing down, or lazy 0, we return. Wait, but there's some. What if this is the case here? So we know that this will be filled. We know that the tree will be filled. We know that the tree will be filled. We know that the tree will be filled. There's no need to check this. But there is a need to say that to apply the function. So when we are pushing here, if this is the case, we want to apply, we want to apply the lazy, applying the lazy. Okay, when we push down, the thing is that we apply the lazy, right? But then here, when we update again this function, but okay, then there will be this push, which will I can do this. I can do this, say that this is the case. Okay, so we know the value. We know the value of these bottom nodes. We now want to say what is the value for the merger. And the merger will only happen at top nodes. So okay. We say that how much time do we have? 47 minutes. Well, G I don't think is going to be an easy problem. No, that's not an easy problem. Okay, we can solve D first. Probably faster than F, and then yeah, okay, let's go solve D first. Because D is just implementation. D is just heavy implementation. Okay. There are 3 things to read here. Okay, let's call this like a function here, read. So there's this A. How big was this 4? Okay, let's get the bounding box. So I don't think I had a snippet for that, but I have to make a snippet for that. So x minimum x maximum y minimum y maximum. So there's if a j is equal to this, what is this? Okay, so if this is equal, x minimum is minimum. Is it guaranteed that the given ball? Yes, they're not there. X minimum and I x maximum x maximum y minimum j y maximum maximum j. That's the bounding box, and then there should be a vector of strings of some. I don't think I needed the bounding box, but that it will make it, I think, a lot faster. Vector string y, let's say result is the x maximum minus x minimum plus 1, and then we go and we say that we go from the x minimum to the x maximum, and then we go to the from the y minimum to the y maximum. These are included. Rest at I minus x minimum dot push back a of I and j. The rest. Now we need another function. If this is bigger than 16, then it's impossible. And now we need to just brute force over the, oh, the rotations would be very, very difficult for non for on this, mate. I think it will be even. I think it will be fast without this here. Because I already have some rotation thing. I will do this. Then I will say I think this will be even fast. Okay, so the rotation. There's this rotate mat thing, but instead of this, I'll just put a string here, so I can quickly easily rotate that. Okay, this is in place rotation. So for rotation of the A matrix, rotation for all 4 rotations, for rotation on the B matrix, for rotation on the C matrix. Okay, and then I need to know the position of this A matrix. Wait, all squares of the grid are covered in polynomial. So all squares of the grid must be covered. So what I will do is I'll create a function. I will create a sum function. It's like put matrix A and call this function that will get me some matrix. So this is string empty. Put location, so put matrix A, the empty matrix, and we get out some new matrix, and then we return put B with the new matrix, and then we get another matrix. Then we return put C with the new matrix, matrix 1. Then we get another matrix back. then here we return true. So like nested lambda functions. But this lambda function will be, I mean, it isn't lambda function, it's just, yeah, it's kind of, but, okay, so bool put, it's like one matrix to put. This is like base, and then there's a function that should return boolean but accepts a string matrix now for each of my positions where I will put it, I will put, so I need 1, 2, 3 positions up. So from -3 to 4, -3 to 4. So we put this matrix here on the base matrix. So we say like this: if I is smaller than 0 or j smaller than 0, both of these are the case, and to put matrix, oh, of course, we need to iterate here again 4 times. If I is smaller than 0 or j smaller than 0, and then the matrix to put at KL is this, then we just want to fail is true. Okay, so if it's not fail, we can put it there. Okay, so that can fail, but also if now else, so if it's not there, it's there. So if to put KL is this, and the base at I plus k and j plus k, I plus k, j plus k, if the base there is, so to put is there, the base is there is this, then fails true. So this says that I can put it there, so I put it there. So I make copy of the base, and then I put it there. So we say copy if to put KL is copy at K at copy at I plus K J plus L is also this. Now that we know we have the copy, we can call the function f. If function if recursion of now the if recursion and then this is the copy, if recursion of this is correct, then we want to say that return true. Now we have to check here, is the whole matrix filled? It will be filled if from lambda string allocator math return false. Boolean, right, that's fine. Boolean return true here. To function Boolean vector allocator type. Do you need to define like a function here? What is he doing? Print accept. That's a Boolean function. What? Let me just return a copy here. Okay, somewhere it crashes, which means indexing is not right. So these are practically null, right? So when there is yes, it's crashing the indexing something. Let's see. -3, -3. If this is smaller than 0 and this is staying here, this copy and I plus k is bigger or equal to 0 and j plus l is bigger than or equal to 0. This is this is L. This is L here. Let me just check out here everything. If this or this is smaller than 0, break here. Okay, so let me just print out what is. Oh, okay. Oh yeah, and I plus k has to be smaller than 4 and j plus k has to be smaller than 4. Here also if the case is that this is bigger than 4, bigger or equal than 4, then we have to check as well this, right? The received output, yes, wait, what? How, yes? This, then this is rotated once. Excuse me, what? How is this? No, may not be flipped. Are we flipping it? Yeah, okay, so this is supposed to be yes. C doesn't really matter, right? I mean, C doesn't matter. I'm more interested in B. Wait, okay. So, wait, what? No, C doesn't really matter. I'm more interested in B. Oh, it is rotated. Wait, huh? B is not rotated. B is not rotated, which means it fits like this. Somehow. What? Oh, what? How many times do I have to make mistakes on the indices? Okay, I'm so hungry. No, please don't fail. Yes, oh, okay, got accepted. Okay, so now F. I think F it could be just standard. This lazy segment tree. Yeah, I lost a lot of time because I tried to solve F. But okay, so we apply the operation. The merging should be simple. Lazy doesn't change. The suffix of 0 and the suffix of 1. So the suffix of 0 is updated such that when we have a sum suffix, if this suffix is the whole size, in the whole tree, then we can update something more here. If the prefix is the whole tree, then we can update something more here. So okay, so there's no way why we can't do if suffix is 0 is the whole wait, no, if this suffix is L dot size, then we can make it more. Of that size, then my suffix here is my suffix is the best out of so wait, my suffix is L. Suffix 1 is pref R. The prefix is L. Prefix 0. Prefix 1. L. So okay, so we update the suffix and we say that if prefix of 0 is equal to the L dot size, it means that it fills up the L positions, then we can prefix of 0 L0, we can prefix of 0, we can maximize prefix of 0 and prefix of 0 plus R prefix of 0. And then this is now if R sub. Okay, so another thing is once again this can be now this is if suffix is R dot size, then we can maximize the suffix with this with L suffixes. This will be positive, so it doesn't actually need a maximization function. Okay, so we now know what is a suffix and what is this. The value is always like value is maximum of. So there are two values. There's this value of having zeros and value of having ones actually. So that's not actually that good. Okay, so value of 0 and value of 1 is switched. Lazy switched, lazy switch, blah blah blah. Okay, here return the value. Well, there is a problem now. We want to return we have to merge them. We can't just do this. We have to merge these two nodes. Oh, this will be pain in the... Wait, is it without like there's lazy? There's this lazy segment tree that I have that actually is much better without the sparse thing. Wait, let's try this. I have 10 minutes. I don't want to call it. Okay, so there's this lazy segment tree that does an interesting job over here with the it's a little bit more complicated, but coded this back then very quickly for some contest and then got to update it. Need to update it. And the thing is that there's this value again of 0 and 1. Then there's this lazy. Then there's this prefix, suffix, now how do you merge it? It's a whole different story. Okay, so when I want to put here something, it's like I put in position I what s of I minus 0. If s of I, then I put 1. So then okay, so if what is like value of one of value sec index dot value is 0 0 sec index value, this is what we want to put in there. Okay, if lazy do we want to swap the values 0 and values 1? Yeah, we do want to swap them. We want also to swap the prefix and the suffixes. So that's another thing we want to swap. If it's not this, then this will be propagated. Lazy will be put to 0, yes, of course. Okay, so this is then the merging. 5 minutes. The merging. Okay, so value. I don't know how to merge. Lazy, I know how to merge. Prefix is well, not this. In new prefix int new prefix is prefix at my node. So this is the left node I have. So prefix 0, prefix 1. Int new suffix is suffix other dot suffix of 0 other dot suffix 1. Okay, if now we need to know the size of the node. But no. Yes, we need to know the size. Okay, if prefix is 0, so if the prefix is equal to the size, then new prefix is 0, other prefix is 0. If other dot suffix is 0 is equal to other dot size, then new suffix is 0 plus equal to suffix. That's again for 1. And okay, so now we have new and then the value of 0 is the maximum between. So wait, so think this new values, int new value is the value maximum of value of 0. Actually, three things: value of 0, other that value of 0, new prefix 0, new suffix of 0. And this is the same idea but with 1. And now we just new value, lazy new prefix, new suffix. Okay. What now? What is this? Come on, like that's why I hate these arrays. What? The pointer cannot be used to initialize the array, so can I just use vectors instead? Now that we term, can I do this? Tree dot, come on, tree dot update range r, tree dot ask range. I don't have time to debug it. Come on. I'll be very disappointed if this works from the first try, even though the competition has ended, but okay, yes, it doesn't work. But that's because we update the range. Yes, okay, we do update the range properly. We do. I mean, it's only a matter of time when the wait. What is the end dot value? This, and I want to see end dot values. Yeah, it's something to do with these kind of merges here. Merges. Totally weird, but okay. Yeah, I'm not sure. Yeah, the lazy is never propagated properly. Like, yeah, we need a couple of things to file down, but that's essentially it for me. Could probably solve F if I have more time. And D was heavy implementation. We could have solved it much quicker because we spent time on F. It's just that. But yeah, I hope you learned something, and I will see you in the in the next AtCoder or Codeforce round. Thanks for watching.